Presentation is a bit about using the new Casper system for data analysis and visualization, which is the main intent of the system, just like with the older systems, Geyser, Caldera, and the sometimes mentioned Pronghorn. So my name is Brian Vanderwen. I think most people in here anyway know me. I'm in the consulting services group, and I've been giving quite a few of these tutorials over the past couple of years. I wanted to put a picture of the friendly ghost on this title slide, but I wasn't sure about copyright, so I just made a semi-transparent picture of the city. Close enough. Point. Okay, so here are the main kind of topic areas that I want to cover today. We'll talk a bit about the hardware. Casper is a bit more heterogeneous than the other systems that we've brought in. There's 4 different node types encompassed in Casper, so if you say to yourself, I want a Casper node, that's a bit more complicated. It doesn't necessarily mean, or it won't mean, one particular type or one particular collection of hardware. There's a variety. We'll talk a bit about how to access those resources using the Slurm scheduler. Talk about interactive jobs and also virtual remote desktops, which is definitely the better way to do graphical user interface applications because it's more snappy than doing it natively. And then using the GPU capabilities of Casper, which are more significant than our prior systems. So let's start with an overview of the hardware. So Casper, of course, is the latest data analysis and visualization platform that CISL offers. And I'm going to use this acronym DAV fairly frequently in this presentation. So just know when I say DAV, I'm talking about Casper, I'm talking about Caldera, Geyser, Pronghorn. At the end of the year, I'll be talking about Casper only. So Casper provides a modern Intel Xeon architecture like all of our other systems right now. It's the Skylake processors, if you're curious. It has a high memory footprint, so it's certainly high relative to Cheyenne. It's comparable to Geyser, at least some of the nodes. And then, of course, like our other GPU accelerated systems, it offers OpenGL rendering for things like Vapor. Some of the nodes have NVIDIA GPUs for visualization, and we also have some nodes that are kind of tailored for machine deep learning neural networks, which is certainly a growth area of interest here at NCAR and in the university community. And an important thing to remember, and we'll be talking about this, of course, over the next couple months and reminding you all that Geyser and Caldera will be decommissioned at the end of 2018. So we have a period of overlap time here with the systems, but it's a good idea to start thinking and planning ahead with the idea that Casper will be your main location for doing data analysis and visualization work. So as I said, there are 4 different types of Casper nodes, and this was designed with the idea to enable varied workflow. We've noticed that people do all sorts of different things on the data analysis machines, some of which use a lot of memory, some of which use GPUs, and some of which are just kind of more standard data analysis workflows. So with that in mind, we have these 4 node types. There are 12 nodes that have no GPUs. They have 384 gigabytes of memory. And all of the node types have 36 2.3 gigahertz Xeon 36 core processors, or I guess 18 core processors, 2 of them, 2 sockets. These are really the workhorse data analysis and processing nodes. So if you have a quote-unquote simple workflow, I would just target these because there are the most of them and you're probably going to get on them the quickest. But if you want a GPU, let's say you want to do some visualization, but you're not really doing number crunching or computation, we have these 8 nodes which look similar to these 12, same memory footprint, but they each have one NVIDIA Quadro GP100 GPU. And these GPUs, again, are quite capable of rendering and doing some GPU work, but they're not as powerful as these 2 collections of nodes.
Probably these are still more powerful than Caldera's.
Than the Teslas?
Yeah, I think.
By far. Yeah. Yeah, so it's still, you know.
So you can still do, you know, GPU work there.
Absolutely, yeah. If you're going from the Teslas on Caldera, you know, you'll be well off on there. It's just these aren't the true powerhouses. Thanks. That's a good point. So in terms of the I wrote Tesla there. In terms of the Voltas, I'll fix that. There are 4 nodes, and 2 of them have 4 Volta GPUs. Sorry about that. Per node. These are connected via NVLink as well, which gives you a very fast connection between the GPUs themselves. This particular collection of 2 nodes has 768 gigabytes of memory, and our intention there is for really, again, for machine learning, deep learning applications, obviously also GPU applications where you're doing you know, things like, let's say, running the GPU-enabled MPAS would be a nice thing to play with on there. And then we have these 2 nodes, which have even more memory, over 1 terabyte each, and then 8 Volta 100 GPUs. So here, you know, you could do highly parallel GPU applications. Now, obviously, there's only 2 of each of these, so if you're requesting them and they get popular, then you might have more of a weight than if you have more general request on Casper. So I wouldn't do like just an NCL script on these nodes, because it's not going to be the best place for them unless you have an incredible memory requirement. But even there, there are ways to do those on these nodes as well. Yes?
Just a quick question. Is there a mechanism for a user to constrain themselves to any of these sets of nodes?
Yes. And I'm gonna get there soon. But thank you. Before I do that, though, just to give some general information for all of these Casper nodes, regardless of the flavor, they all use the existing Geyser Caldera environment modules. So when we compiled the different software that we offer using module avail, all of that stuff looks exactly the same across the different data analysis nodes. And that's enabled because, as we talked about right before starting the presentation, they all run the same version of the CentOS operating system. So the environment should look very similar across all of the nodes, which should make things pretty convenient. Now, just like with the existing DAV systems, the modules are not shared with Cheyenne, so your environment is cleaned when you go from Cheyenne to DAV. That's, you know, I think everybody's probably pretty used to that at this point, but it's certainly something to be aware of when you're going from the SUSE Linux on Cheyenne to the CentOS Linux on DAV. So with that in mind, I would say it's a good idea to compile your code on the same system that you will use to run. And I would go as far as to say, if you have code that you compiled on Geyser, for example, just go ahead and recompile it on Casper. You know, that's not strictly required, but I think you'll see better performance with the newer CPU architecture. Certainly if you're doing GPU code, there are newer versions of CUDA that we've set up for when we brought Casper in. So recompiling there is definitely a good idea. And if you have code that you've compiled on Cheyenne, definitely recompile it or compile a second version to run on the DAV systems. Yeah. And just like the other DAV machines, both Glade and the tape archive are accessible from Casper, as well as the campaign storage through the Globus command line interface. So all of our storage platforms, our main storage platforms, are available on these nodes, are accessible on these nodes. One interesting thing about the Casper nodes is that they have this NVMe solid-state storage, and this provides high I/O performance node local storage. So this storage is not globally accessible like Glade, but it's local to the node that you're on. So each node has 2 terabytes of the solid-state storage, and some of that is reserved and used to augment memory. And this is nice because if you go over the memory limit on the node, or the memory that you've even requested from Slurm, it's less likely that your job will fail because of excess memory use. That's kind of used as a buffer. Now, obviously, there's still an upper limit. There's still a hardware limit, so you know, be conscious of memory. But hopefully we'll see less memory failures for jobs because of this overflow memory-like place. Now there's also a segment of the solid state storage that's given to jobs. So the Casper jobs, each job has access to NVMe storage in this directory that you would see in your root path. It's /local_scratch/ and then your Slurm job ID. So you could just use that environment variable in your job. And that'll give you a space where you can, if you want, you can move some of your data onto that NVMe storage and then run operations there. And depending on the way your workflow is set up, that may give you some performance benefit. Now, of course, you have to balance that with the time it takes to copy the data over and, if necessary, copy data back. So it's a, it's a balance. But that's another resource you have in your jobs.
Is that purged as soon as your job ends?
Yep. I was just putting that bullet up in red even. No. This is good questions. Yeah, so the data that's stored in that space is deleted when the job ends. So, be very aware.
So, how big is the space for each job? Can we use for the?
I'd have to look. I think for all jobs it's over 100 gigabytes, I believe. But if you run the df command with a -h, you can get the human readable format and see how much is in that that file space.
So basically the space is shared among all the users of Casper.
Yeah, and it's subdivided into the job directories, so that's how you handle permissions, but in terms of the available storage, it's shared.
Okay. So there is no quota at the moment?
I don't believe so, but that's something we should check with the systems group. This has not been too exercised yet. I mean, I've played around with it in certain workflows. Like there was this NCL script, and it was fast, and it was useful to move data into there. But in terms of those fine details, I think need to play around a little bit. And I'm going to, I don't want to speak for them, but I think that amount that's allocated to all of the jobs, that can be tweaked if it looks like it's being, if it's popular, or if we need more memory to augment, or more storage to augment the memory. So, okay. So moving on a bit from that, I'm going to talk about accessing Casper resources using the Slurm scheduler. And this is where I'll address how to constrain where your job goes. So all of the DAV resources, including Casper, are requested via the Slurm scheduler. This is something that anybody who's been using the systems should be pretty used to at this point. So Casper, Geyser, Caldera, and Pronghorn, they're all included in this DAV partition, and in Slurm terminology, a partition is the same as an LSF or PBS queue. In this DAV partition, we allow wall times up to 24 hours, so double the maximum length of a Cheyenne job. Obviously, if you request less, you're more likely to get your job through quickly, so don't just default to 24 hours, but that's the default max. And then the best practice, I would say, is to request specific resources and features, and then let Slurm choose an appropriate node. So this is a bit of a shift in philosophy from the past where, we've really said, okay, well, if you hop on Geyser, just ask for, a Geyser node, or back in the day, ask for the Geyser queue, and then you'll end up there. But since Casper is heterogeneous and has these different node types, I think it's a better idea to ask for the features that you want and just let the scheduler handle it, and you'll end up there a little quicker. Yeah, shorter queue times. That's always our goal. So Casper batch jobs are submitted from Cheyenne using the sbatch command, and I'll just show an example script here. This should, again, look very familiar. So here I've got a basic C shell batch script, and I'm in this example script, I'm running an NCL script. Again, the DAV partition, I'm asking for 10 minutes, so hours, minutes, seconds. I'm asking for one task, and I'm asking for 6 gigabytes of memory to be allocated to this job. As always, we suggest that you set the temporary directory so that you don't run into issues with the limited amount of temp space that's local to the node. So then I load the NCL module, I run my script, and some people have asked this in tickets, if you want some job information, a job summary basically, to show up in your logs, this is a command that you can run to get that. That's kind of similar to what LSF did back in the day, where it would print out a little job summary at the end of the job.
Right.
So that's one way you can manually do that. Yes?
I presume these slides or these examples are going to be shared?
Yeah, the slides will be shared, and these examples are very close to the, or if not the same as the examples that BJ has in our documentation pages now. So, yeah.
So that show job shows also the script itself, like LSF did?
No, it doesn't show the script.
Okay.
So it's not a one-to-one comparison, but it will show things like approximate maximum memory usage, CPU, what nodes the job landed on, how long the job took. So yeah, it's not the same, but it should provide some useful information. So, for the bash version of this, one thing I want to point out is that your header line where you invoke the shell, you want to have this -L option that tells the scheduler, that tells the job environment to use a login environment, which basically will load all the startup scripts. And if you don't have that -L, then you won't have access to things like the module system. So that's something that's tripped some folks up. In the past, we used these Slurm init scripts. We've deprecated these when we moved away from when we brought things online in the spring. So when we moved to CentOS, basically. So don't put these in there anymore. I don't think they exist anymore. So if you have them in your old scripts, you'll get an error when you try to source them. If you don't know what I'm talking about, don't worry about it. Just follow this example, or the bash example. Now, I'm talking about Casper here, but if you look at the script, I'm not specifying Casper anywhere. And in fact, this example will run on any node, any DAV node, with 1 core and 6 gigabytes of memory available. So I'm being a little deceitful here. This isn't necessarily a Casper example, but it gets to my point of asking for resources instead of a system, because you'll get your job scheduled more quickly. But, you might want to hop on a Casper node, and there are multiple ways to do that. So this is where I get into restricting the job placement using what Slurm calls feature constraints and what Slurm calls consumable resources. And these are two different approaches. So first, let's talk about these feature constraints. So this would be an sbatch directive at the top of your job script with a $C, and then the feature that you want to constrain your job to. So in this case, one example would be a GPU constraint, which perhaps is obvious, constrains your job to land on a node with a GPU. Now that still doesn't necessarily get you on Casper, because Geyser and Caldera both have GPUs as well. But you won't land on Pronghorn, or you won't land on the subset of Casper nodes that don't have GPUs. So the feature constraint specifies nodes that must have that attribute. It's not consumptive, which means that if I ask for a GPU on a node, I'm not exclusively using that GPU and preventing other folks from using that GPU. So this is basically just saying I want to be on a node where I have the capability of using a GPU, but I'm not reserving it for myself. That's a feature constraint. And these feature constraints allow for Boolean logic as well, with and or here. This is just an ampersand and a vertical line. And you can put those in here. It's a good idea to put this string in quotes if you use the feature constraints. But that's a way I could say I want it to have a GPU and Skylake CPUs, for example. So I can further constrain my job. Yes?
You have not in your Boolean. If you have and or, is not available, like not GPU or not B100?
I'd have to check the manual page. We could do that. I have the terminal up here. So let's look up. Here we go, constraint. So and or and matching or. Yeah, so it doesn't look like it. But hopefully we've provided enough of these constraints that you can kind of get it what you need. And if there's some combination of resources that you need that we're not enabling with our constraints that I'll show the list of in a bit, let us know. So then there's these generic consumable resources, and this is with this sbatch-gres option. So, and in this example, I'm saying I want a generic consumable resource. It's of type GPU. The GPU is a Volta 100, and I want 2 of them. Now, this is just adding restrictions with these colons. So I could just say gres equals GPU, and then I get a GPU of any type. Or I could say a V100 and leave the 2 off, and then it defaults to a single GPU. Now, the difference here is that these resources are exclusive to the job step. And a Slurm job step would be like an sbatch command or an srun command. So when I say that I want that consumable resource in that call to Slurm, I'm saying that call is the only thing, ideally, that can use that resource. So that's the difference between a feature constraint and a consumable resource. Now, of course, make sure that your feature constraints and resource requests agree. If you over here ask for a V100 constraint, and then you say you want GP100 consumable resource GPUs here, that's not going to work because we don't have any nodes that have both of those GPUs on them. And I don't think Slurm will tell you it can't do it. Slurm will schedule the job, or will queue the job, and then just let the job sit there in the hopes that someday we add that hardware.
Like it.
Which isn't going to happen, so probably. So it's a good thing to check when you're submitting. And if you have scripts, then to have those scripts, like check those scripts before you run them. Otherwise, you'll have lots of jobs that will never get dispatched. So here's a summary of our current offerings on DAV and the features and resources that they have. So let's start with the older hardware. And these counts are ideal. Since we're getting to the end of life on Caldera and Pronghorn and Geyser, nodes are kind of going in and out, sometimes just out. So these numbers they're on the high end. But
yeah, I think some of them are definitely dead now.
Yeah, we've lost a couple of Geyser nodes, for example, so I can tell you this isn't 16. But that's what you would see listed if you ran a node count in Slurm. So Caldera, we had 16, and Caldera and Pronghorn both use Sandy Bridge Intel chips. Geyser uses Westmere, and then the Casper uses Skylake chips. So these are all feature constraints, and you can specify where you want to land based on the CPU architecture, for example. You could specify where you want your jobs to land with this GPU constraint, which will place you on any node with a GPU. We also have this X11 constraint, which logically places you on a node where you can run X11 applications. Now, since this is a little more interesting because the newer virtual desktops like GNOME 3 and the newer versions of KDE are GPU accelerated. So that kind of restricts this a bit to saying, let's have X11 virtual desktops run on nodes with GPUs. So that's kind of the way we've set this up. So if you use that X11 constraint, you'll land on one of those 3 types. And X11 infrastructure wasn't installed on these machine learning GPU intensive nodes just because we don't really want those jobs to go there. That's not their purpose. So you wouldn't run like a VNC virtual desktop on these 2 nodes, or these 2 node types. And then the exact GPU type is also specifiable. And there's this further constraint, this 4x V100 and 8x V100, which is how you can constrain yourself to a count of the V100s being available on the Casper nodes. Now, I didn't list it over here, but the node name is also a feature constraint. So if I do want to say constrain to Casper, I can still do that. It's just I'm not sure which of the 4 flavors of Casper I'm going to end up on. So it's better to specify, I think, a hardware feature here.
It's equivalent to specify Skylake, basically.
Yeah. Specifying Skylake and Casper would be the same at the moment. you know,
But it might change.
that might change. Yeah, if we add new nodes to Casper at some point, you know, they might be Cannon Lake or some, you know, whatever Intel has out at the time. But yeah, at the moment, that's true. And then for the consumable resources, right now, our only consumable resource on the nodes is the GPUs, and that is only limited by the number of them. So on Caldera, there's 2 GPUs available. On Geyser, there's 1. On these Casper nodes, there's 1 GPU 100 per node, and on these, there's up to 4 and up to 8.
So is that just a tiny little typo in the Caldera wants to be GPU K20 122?
Ah, yes. Thank you. I'll fix that in the actual slides, but thank you for pointing that out. Okay. So now let's talk a little bit about running interactive and graphical jobs on Casper. So as before, we're providing this helper script to initiate interactive sessions on the analysis systems. Currently, we have execdav, execga, GY, and execca for Geyser and Caldera. We're not doing a specific one for Casper because, again, we want to kind of get towards a more resource-focused model here, I think. So you can use execdav to get on any of them. The basic syntax here is you run execdav -a and then give your project or account code. Now, yeah? Oh, okay. And then there's a few other options. The ones I want to highlight, -t, you can give the time, just like in a batch script, and it's hours, minutes, seconds. -n for the number of cores or tasks in the session. -m to specify a memory request. Again, if you go up to about 1,100 gigabytes, that's reasonable because we have these very large Casper nodes that can accommodate that. But obviously, that restricts the types of nodes that your job can land on. So, you know, don't just aim as high as you can.
Well, plus, if you're doing this interactively, you're going to have a long waiting queue. So you say, exec this, and then you're just waiting there forever to jump. So.
Exactly. Yeah, that's a good point. I would be as minimal with your requests as you can with the exec version, because otherwise you may be sitting there waiting for a little while, and nobody enjoys that.
So then do you have a good way of estimating how much memory you're going to need in your job? I mean, you got to just run it once with some big...
Yeah,
Is there a report that tells you memory high watermark?
Yeah, so unfortunately you do have to run it once if you don't have an idea of what you need, but you can get an approximate amount from Slurm. Slurm will give you that when you run the job. And if you want to get a little more fine-grained, Davide wrote this peak mem usage utility, which you can run the application with, and that will give you a report, I think at a thread level, right, if you have a multi-threaded application?
Yeah, well, at thread level, but at thread level memory is shared, so it can do that, so it's kind of useless.
Yeah, or at least at a process
actually
level.
At process level. I mean, it does both.
Yeah. But, you know, if you have no idea going into it, I mean, you can kind of estimate based on the size of your data structures and stuff, but, you know, that's...
Well, if I'm going to run MATLAB or something on there, I got no idea how much that interactive application is going to be taking.
Yeah, I mean, that kind of just comes on your experience with the workflow initially, but then after you run it once, you should have some idea from the Slurm report. Okay. And then if you want X11 support, that depends firstly on your login node session. So you have to log into Cheyenne with X support using either -X or if you're on a Mac, -Y. To get that on the login node, and then this script will detect that and say, okay, enable this in the DAV session as well. Now, you have to end up on a node that has that X11 support as well. So there's kind of 2 requirements there to use X in a data analysis session. Now, that said, I would personally recommend using Turbo VNC to do a virtual desktop rather than running an X application natively, because it's just going to be snappier and more responsive, and I think a more friendly user experience. You know, things like running the Vapor GUI or IDL or MATLAB's IDE, I would do those, if possible, in a VNC session. So VNC, it provides a remote GNOME 3 or KDE desktop. I don't personally love GNOME 3, but that's where things are going, so I'm getting used to it slowly. the way that you specify this, we have this VNC server submit script. We've had this for a while. And you can specify your project code to it, just like with the execdav. And then you can specify the type of desktop you want. Right now, it's GNOME or KDE.
So does that have a default GNOME?
Yeah, it defaults to GNOME, yeah. So KDE would be, an option if you don't want to use GNOME, but that's where it'll default. And one nice thing with VNC as well is that you can reconnect to a VNC desktop as long as the Slurm job that is hosting that desktop is still active. So if you have, say, a 12-hour Slurm job, you do some work in your desktop and then you close the desktop out, as long as that job's still running 4 hours later, you can go back to your desktop and all of your windows and everything should still be open. So that's certainly a convenience, I would say. So let's show that one off just to see what you get. So you can run that VNC server submit script from either Cheyenne or from the data analysis nodes. So it should be location independent. I'm going to put my project code in there. And let's try KDE just for fun. Now this script, I've tweaked it a little bit recently, so if you haven't run it in the past 2 months, it'll look a little bit different. But the general process is the same. We have VNC submit a job to Slurm. Wait for that job to start. And then you have to establish an SSH tunnel, which is kind of the one little annoying bit here. So I'll go into a separate screen, paste that.
Separate screen on your laptop?
Yes, a separate local terminal session, not a separate Cheyenne session. This is, we're just running on my local screen. In Windows, you might have to use something like PuTTY. I would personally recommend using something like MOBA Xterm or something like that, just because it's a little more native and friendly, I think. So then we get these instructions here. This is another thing. If you have a different VNC application, we find that they typically don't work nicely. So I would just download the Turbo VNC application and use that one specifically. So we'll put the local host with the port number in there. And then it's going to ask for this one-time password. Again, it's a one-time password, so it works once. But if I recreate that tunnel, if I run that tunnel command again, I'll get a new one-time password. So, and I've lost track of where I've typed that. So let's see, 1802758.
Boom.
And there we go. Now I've got my KDE desktop here. Pretty bare bones because I don't do anything in KDE. I don't have any desktop customization. But here I am. And I could open up a terminal here. One interesting thing is you have some GNOME applications as well as the KDE applications.
As well as Vanilla X.
Yeah, as well as Vanilla X. So there's a lot of stuff installed there, and I guess take your preference after you get to the desktop. So at this point I could module load IDL and run IDL-DE. And this isn't the lightest weight application, so it still takes a little time to load, but it's certainly faster and more responsive than it would be just running it with X. Oh, that disappeared. Bummer. I think that might be a thread thing. Live demos. All right, we'll get that straightened out. But I'm going to close out of that desktop. It's a good idea to always kill the tunnel when you're done. And then it's definitely a good idea when you're back on Cheyenne to cancel your Slurm job when you're done with your desktop completely. Otherwise, you're just using up core hours for something that's not doing anything. Okay.
So that's a good idea both for your location and for making resources available to other people who might be waiting for them.
Yeah, you're also being a good supercomputing citizen when you're killing your jobs that you're not using anymore. And yeah, it's typically faster, more responsive than X11. So the last thing I want to briefly talk about is making use of the GPU capabilities on Casper. And this is only one small aspect of it, but it should be enough to get you at least started. So Basically, I just want to talk about if you're running, say, GPU code that you have, like let's say some CUDA code, how would you go through setting that up? So let's say I have some CUDA code that I want to compile and run. This is serial code in this example, so I'm going to use a single GPU in a single task. The NVIDIA drivers and the CUDA SDK are all installed and usable on any node with a GPU. So what I would do is I would run an execdav, and I would constrain myself to a Casper node that has a GPU. Then I would load the CUDA SDK. I'm assuming here I already have a compiler loaded. It could be Intel, PGI, GNU. And then I'm going to use the NVIDIA CUDA compiler and VCC to create my binary, and then I can just run it. And since I have access to the GPU on the GPU node, should be good to go. Now, if I want exclusive use of that GPU, then that's where the generic consumable resource should come in. But if I'm just running like a hello world, then I can share that GPU with people and not have a problem.
So do we have an example of that consumable resource? Because I know my interns got confused about that last summer, and we didn't have all the setup in place at the time. But
I don't think we have an example that combines the consumable resource with the compiling. We could add that, but there are examples of the consumable resources, and there are examples of the compiling.
Okay.
Then the parallel example here, this would be compiling multi-GPU MPI-CUDA code. Again, here I go on to an appropriate node. Now I'm loading both the CUDA SDK and an MPI implementation. Our default one on there right now is OpenMPI. Now I'm going to compile my CUDA code with the NVIDIA compiler, and then I'm going to compile my MPI-C code with MPI-CC. And then I link everything together, this GPU object and then the main C object here into my binary. Now this obviously can have many different appearances based on the structure of your code, but this is just a very simple example.
I'm kind of confused about the number of tasks that you can run by default. So you said that one is the default for execdav, right?
Yes.
So how I make sure that my multiple tasks are running on different GPUs?
Right. So that's why I didn't put the run command on the slide.
Okay.
Because the way I personally would do this is I would go into a single task session here, do all my compilation, and then submit a batch script, which in this case I'm going to request 2 tasks. I think you're asking how do you specify the number of GPUs?
The number of GPUs, to use for each process, basically.
For each process?
Yeah. Because, for example, by default, I don't know what Casper and GPU does in terms of GPU assignment. I think it's just one, right?
I believe so, yeah. I think it's 1 per task, 1 per MPI task.
1 per task, okay. Makes sense.
Yeah, and I'd have to look a little bit more into the.
Okay.
We probably have some folks in the room who could answer that question better, but yeah, I'm just kind of getting at it from the setting up the job perspective.
It's okay.
But it's a good point. So for running it, I would run it in a batch script just because there I can easily control my available resources anyway. So here in this job, I'm asking for 2 tasks, 2 MPI tasks across 2 nodes, so it'll be 1 task per node. Each of these is going to have the 1 GP100 GPU. And then here I again have to load the OpenMPI and CUDA modules, and then I srun my program, and that's because I'm running with MPI. Now again here I'm using a feature constraint instead of a consumable resource, so I'm sharing the GPU with others. And I also want to mention real quick that we have, and this is kind of, I hesitate to use the term beta. It's been exercised some, but I imagine there's probably some kinks in there to figure out. But we do have a Python library for machine and deep learning, and I use library in the sense of our NCAR Python library, PyLib. So it's a collection of Python modules that we've installed. The way to get at this, you would do an execdav, constrain yourself to one of the V100 nodes, load Python 364. This is a Python 3 thing. And then there's this version of our Python library. It's 2018-0801 -- DL in caps. So then you can start Python your favorite way with Python or IPython or a Jupyter notebook. And in there we have Google's TensorFlow, we have PyTorch, we have Keras, scikit-learn, among some of our usual Python libraries, like NumPy, of course. So it's a pretty extensive stack at this point, and it's seen some, like I said, it's seen some use in testing, and it seemed to perform pretty well. So I would say play around with that and send us feedback on.
So is the
how that looks.
TensorFlow the GPU version of the CPU version?
It's the GPU version.
So then you also have to load CUDA 9.0.
Yeah.
Module.
Sorry, that's a good point. If you want to use the GPU accelerator, I believe PyTorch is as well. You'd want to load the CUDA SDK.
Right, but TensorFlow doesn't work with the default CUDA, which is I think 9.2. It works with the oldest 9. 9.0. Is it 9 or is it 6? But anyway, the dot 0. The dot 0, not the dot 2.
Yeah.
Yeah, I think we'll probably add some website documentation to make that explicit. But that's a good point. Okay, so some potential stumbling points, in my opinion. So we've kind of talked about this before, but if you start a shell like a bash or a TCSH with srun, which the execdav script does, under the covers, it's allocating using salloc, and then it's using srun to start a terminal session for you. That terminal session is going to use one core. Slurm allocates a core to it. So you would want to ask for n+1 tasks or cores if you wish to start n tasks in that session. So if I want to run an MPI, for example, in an interactive session, and I want to use 4 tasks, I should ask for 5 from execdav, because one of those tasks will be used for the terminal. That's just the way Slurm reserves resources for you. Similarly, if you request a generic consumable resource using gres, and you specify that to srun when starting a terminal, those GPU resources won't be available for subsequent srun commands. This is definitely a tripping point. So if I specify a gres to my terminal and I say I want 2 GPUs, all of a sudden those 2 GPUs are getting used, quote unquote, to run the terminal. They're not actually, but that's what Slurm is reserving them for. So I couldn't use those in an MPI call. So you need to be careful about where you specify those gres settings. That's why doing these things in an sbatch, I think, a lot of times is easier, because...
So these are only for interactive, these stumbling points? How about if I have a script that has 2 subsequent sruns?
Yes.
Would that work?
It's the same thing if you have 2 subsequent sruns. The first srun will reserve its resources, and whatever is left over for the second srun.
So it might be nothing because...
Possibly nothing, yeah.
So I might need a different job.
Exactly.
Use 2 jobs. Is there another alternative instead of running 2 jobs if I have 2 srun commands that I want to run?
Well, an alternative would be, I could go on a node that has 4 GPUs and have each srun ask for 2.
And then should I background the first, since maybe I want them to run more efficiently?
Yeah, you could. So yeah, that second point is definitely something you need to be aware of in batch scripts as well. The first point only applies to terminal sessions.
Quick question to expand on that. In such a case, where you're not actually running a parallel MPI job on multiple GPUs, should a responsible user restrict themselves to the GPU 100s? Because instead what you're doing is grabbing one of 4 very expensive nodes, I assume, with NVLink, meant to be a multi-process MPI application and incorporate multi-GPUs. So if you truly just have sets of serial jobs, keep them on the GPU 100 nodes, because you're not wasting the NVLink. Yeah?
Yes, I would say that would be a responsible thing to do. And in fact, I would even go maybe a step back and say just, at that point, ask for a Casper GPU and let Slurm put you in a place. And it emphasizes the least common denominator resource. So as long as there's a GPU 100 available, it'll put you there. If there doesn't happen to be one, but there is a Volta available, it'll put you there. So that, I think, plays nicely with others, but also benefits you.
As long as the others don't want all of the GPUs on a monster node, which
Yeah.
is what I'd call the V100 node.
Yeah, that's true. That's true. And then finally, I mentioned this before as well, but VNC only works on nodes with the X11 feature. I've had a ticket or two about this, and that's kind of a little different than it was before we had Casper, so just something to be aware of. And in that VNC server submit script, I specify an X11 constraint. So this isn't something you should ever run into unless you get real heavy on customization when running that script. Okay, so I want to, since we're kind of towards the end of the time, I want to put my information up here as a reference. I do have a little Jupyter Notebook example that I can go through if you want to stick around. That just goes through compiling an MPI-CUDA example. Shouldn't take more than 5 minutes. But if anybody has to go, here's my contact and also our consulting office contact. If you have questions general about Casper, I would say contact the help desk because you'll get a quick response. But if you have specific questions from this presentation today, or if you have feedback that you'd like to give, you can give that to me directly, and I think we'll also have a form that you can fill out. So with that said, thanks for your time. If there are any questions in the room, I can take them now, and also we'll take questions online if they are there.